All right. Kaylee, how do we do it? Okay, top minus bottom, that's it. Like I just have to take like x squared minus x and boom, I have it.
It's the integral of the top function, like the function that goes like over, and then the minus the bottom function that goes.
So the integral of top minus bottom. Okay, does it always have to be top minus bottom, Hannah?
Should always be. Should sometimes.
Wait, no, or volume. Wait, I don't know. Unless
Are we always restricted to just top minus bottom?
No. Oh, you're doing it left or right.
Oh, and would it be right minus left or left minus right? Right minus left. Okay. So we could have the integral from a to b of the upper function minus the lower function dx, or we could have the integral from, let's say, a different set of numbers, c to d, of the right function minus the left function, dy.
Can we turn off the front lights? Sorry, I just can't read it. I'm sorry.
So demanding.
It's just the glare. I can't read it. Is the code word still high maintenance? Yes, the code word is high maintenance. Alright, the code word is high maintenance.
No, it's by the order of the building.
Okay. Let's talk about why one would be beneficial compared to the other. Okay. You guys like integrating with respect to x, but why? What would be a situation in which dy could be good?
The equations are like in terms of y.
When the equations are in terms of y, would be an excellent choice. Whether you can get them into x or not, okay, you might want to just leave them in terms of y. What would be another case? Like, let's say you have an equation, you have a couple of equations in terms of x.
Like if x equals like a constant, like x equals 5, and then it's like a function or something, like the straight lines. I had a thought.
Okay. So what you described is more or less area under one curve instead of like two curves, right? Because with your vertical lines, it's kind of like cutting off like the A and the B. Sorry. I'm gonna call in April since you gave me the other one.
Semicircles, if you do it in terms of x, you have to have like two integrals, and then if you did it in terms of y, you can only do one. You can do one integral.
Okay, so there could be times where we have to break it up into two integrals unless we have it with the y. Is that the example that you
No.
Oh.
I was gonna say like if you had a function like if it was in the quadrant and they were crossing like this, then you'd have to take two integrals, like one from one function to where they intersect and then one from the other function. So then if you put it in terms of y, you could just do right minus left.
Okay, so kind of what you're describing is very similar. Either we have to like write two integrals in terms of x, but then only one integral in terms of y. Okay. So let's just remind ourselves how we do this, okay? And then we'll get to do some examples throughout the class. So in this example, I have y equals x squared and y equals 2x. Okay? If I want the area in between them, a couple things we need to know. We need to know where they intersect. Okay? I also want a picture drawn for us. And I also want the rectangle. Now I know that Mr. Griebel might not have been as super picky as I am about rectangles, but when we get into volume, I want to see that rectangle. Okay, so that rectangle that I drew has thickness dx. It's supposed to be vertical. It doesn't look quite vertical, does it? This is just going to help us know with which variable we're integrating with respect to. Okay, so which x value do we intersect at right here?
0.
So this is 0, 0, and I guess what's this coordinate here? Okay, so we would have the integral from 0 to 2 of our top function 2x minus our bottom function x squared. That is something that I would expect you to integrate by hand and give me the value of without using your calculator. Okay. If we wanted to do this with respect to y, if we wanted to do this with respect to y, then we could draw this rectangle representing the thickness of all those rectangles that we are adding up together. And this time we would be integrating from 0 to 4 because we're integrating with respect to y. And we would need to write our functions in terms of y. So instead of y equals 2x, this green line is x equals y over 2. And instead of y equals x squared, at least this half of our parabola is x equals the positive square root of y. This half over here would be x equals the negative square root of y. Okay? So right minus left, we're going to have the square root of y minus 1/2 y. Here again, you can take the antiderivative and plug in your values to find the area. What should the answer be?
Same.
The same, because we did the same. Okay? I'm just going to show you a picture so we can get to our activity. I'll show you two pictures. Here's a picture of an example where our top and bottom function change. So we would need to have two integrals here. The integral from 0 to pi over 4, and then the integral from pi over 4 to pi over 2. Because the top and the bottom function, they switch. Okay? Here again, in this picture, you would need, if you are integrating with respect to x, right, when we draw in our rectangle, the top function switches here at x equals 2. Okay? Integrating with respect to x, is this our best option in this picture? Okay? We would have to split this into two pieces and find the area of this piece and add it to the area of this piece. If we drew horizontal rectangles with thickness dy, we're consistent with our right function and our left function, so we could just do the integral of right minus left, and we would only have to find one integral as opposed to two and adding them together. Okay, it's all coming back. Okay. All right, so that's going to be half of your problems today. The other half will be volumes by slicing. Okay? Take a moment and just talk about with your pod, do you remember how to do volumes by slicing?
It's like pi minus the square function of the square. You always need a 2 and a pi somewhere.
Yeah.
So it's a 2
No,
pi.
no, the 2 is for the other one.
Yeah, that is for shadow.
Yeah. The
Yeah.
Maybe water tomorrow, shell is Friday.
What are we-
I only remember to squash
Uh-oh.
Oh, wait, volume by where you like.
Is this cross section?
Okay.
Yes.
Oh, this is easy.
That's easy.
Okay. Okay. Volumes of cross sections mean we have our region is like the base of our solid, and then it extends up to some shape. Okay? If we have cross sections perpendicular to the x-axis, we integrate with respect to x. If we have cross sections perpendicular to the y-axis, we integrate with respect to y. So what I'm going to ask you to do, I'm going to ask you to draw your cross section, and the base of it is always lying in your region. Okay, and we'll talk about like what that length is. So you could have an equilateral triangle as a cross section. You could have a semicircle. You could have a square. That would be an easy one, right? So we're taking the area, or excuse me. We're taking the integral of the area, and then dx gives us that thickness for our third dimension for volume, and we add up all of those really thin volumes together. Okay, it's like taking a piece of or a loaf of bread and slicing it, and then we add up all the slices of bread together. Is this coming back? Okay, so okay, so we have x equals 0, 1 minus x over 2, so that's essentially this line right here. 1 minus x over 2. And then negative 1 plus x over 2. So that is this line right here. Okay, so here's our region. I'm going to color it red. That's the region that the base of whatever object we have is sitting on. Okay, and if we are perpendicular to the x-axis, then we have these little rectangles right here. That's our base. And protruding up from that base, it says our equilateral triangles. So this is my suggestion to you. Okay, I'll let you catch up with what you're writing. I'm sorry. What? I am going to.
What did G X it's like
Okay. So first of all, this rectangle right here, if we talk about top minus bottom, we have 1 minus x over 2, and we're subtracting negative 1 plus x over 2. All right? That is the base of whatever shape that we've been given. Okay? So if we subtract those, do you agree that we would get 2 minus x?
Yeah.
So 2 minus x is the base of our triangle in this case. If it was a semicircle, it would be the base of the semicircle. If it was a square, it would be the base of the square. Okay? Our integral is going to go from 0 to 2 because that's where our region is. And we essentially need to write in the area of this this triangle. 1/2 base times height. So we need to know what our base is. Well, we know the base is 2 minus x, right? So now we need to figure out what the height of this triangle is. Okay.
No, that's for something else.
Well, you're not. So radical 3 is going to be involved, yes. So
It's 2 minus x times the radical 3 divided by 2.
okay, so this is half of our base, right? That's 1/2 of 2 minus x. And then the long leg of a 30, 60, 90 triangle would be radical 3 times our small leg. So this is radical 3 times our short leg, which is the base cut in half. Okay? So your radical 3/4, you're thinking of this right here. If we multiply that to here, we would have the radical 3/4. So 2 minus x times, well, I'm going to just make this radical 3/4. And that's pretty. Now this is something I maybe wouldn't make you do without a calculator, as far as the integration. Okay. Setting this up, you can totally do without a calculator. Integrating it might be more work than I would want you to do on like a quiz or test. Yeah, you'd have to multiply it out and then do the reverse power rule and then plug in numbers. You're going from 0 to 2, so the 0 is at least nice to plug in, but I mean, it's not terrible. You could do it.
Could you?
You could. Okay. All right, so I'm going to stop the recording.